Great, thanks. So I'll be talking about this code that I started developing as a graduate student. And kind of like Adam the other day, I started working on this before AstroPy really became widely used. So there's still a lot of work to do, and it's gone through a lot of changes. But in general, what I want to talk about is my philosophy behind the code design and places I hope to take it in the future. Will my clicker work? No. Okay. So for motivation, in terms of science, I study dust scattering. I study interstellar dust with X-ray scattering. I'm trying to play this video now. Great. And to illustrate this, this is a time-lapse image of a magnetar that burst in the X-rays. Now, as you're watching, you see these rings expand. So what's happening is that the X-ray burst is propagating through the interstellar medium, and it's hitting dust clouds along the way. So this is a dust scattering echo. So X-ray light echoes contain a ton of information. When you look at the surface brightness profile, you can fit the dust grain size distribution as well as where it is distributed along the line of sight. And that's not even using the time domain. Okay, so the motivation is that my thesis advisor came up with this wacky idea. What if we could see intergalactic dust with X-ray scattering? So the idea was, all right, we could have some dust outside in galaxy halos through outflows, or we know perhaps there's dust in absorption line systems, or maybe it's just distributed diffusely. And we thought, okay, this dust can kind of be hiding because if it's large, we won't really see it in optical and UV extinction. And X-ray scattering is really sensitive to large dust, so perhaps we could see it with X-ray scattering. So it turns out, for the grain sizes of interest, which are basically more than about 0.1 microns, the approximations that a lot of X-ray astronomers use break down. And this is something that's been known for a long time, but in terms of looking for dust grains that were as big as a micron, people don't normally do that. So I naturally just went to the normal approximation. So when you look at the scattering opacity versus energy, this black line here shows the approximation, which I'll call RG Drude. And then the blue and green solid lines show you what you get when you actually use the exact Lie scattering solution with graphite or silicate, which are two common grain compositions. So as I was doing this, I was actually writing two different IDL functions to do the same thing, but with different scattering models. And at the time, I started learning about Python, and I thought, well, I'd really love to convert all of this stuff to Python. And it really made me think a lot about how I needed to do that. So I decided I want to make my code modular because I'm basically using the same simple equation with just different physics and algorithms. So for example, this is the scattering opacity, which all you need to do is take a dust grain size distribution and integrate it over the cross-section. So not only did I have two different scattering cross-sections that I wanted to use, but I also knew that there's a ton of different grain size distributions you can choose. So here's an example of grain size abundance versus radius for a Zubko Dweck-Arendt model. And these are just two of many models that they have. And you can see that it's all wiggly and complicated. And in addition, they use different grain size compositions. So they have many different combinations of these grain types. And they show a comparison here with a simple power law dust grain size distribution, which we call MRN, which is kind of the canonical go-to for most people. In fact, my code still mostly just uses power laws. So these models were constructed from UV, optical, infrared data, as well as elemental abundance constraints. But in general, there's no X-rays involved in this. So when X-ray astronomers go to look at dust scattering halos, and here's an example of one from the literature, they say, all right, we'll take all of these models, plug them in, and see how it works. So here you see 17 different dust grain models. And these two different tables just represent different spatial distributions of the dust. And all 17 of these models fit relatively the same. So here we have a chi-squared value of about 4 or 5. And then in this one, you have a chi-squared value of about 1 for pretty much all of the models. So all we're really doing here is saying, well, it looks like a single cloud of dust fits pretty good. But we can't tell the difference between the two models. Here's another example for SIGX1 where they put in two different dusts. And this is meant to be information overload, by the way. They take two different positions for clouds, and then they fit 18 dust grain models. And what do you know? They all fit about the same. So we can't really say anything. And I really hate this a lot. I'm just going to say it out loud. Okay, so I look at this and I say, you know, this is great, but these models were made from other wavelength information, and I feel like we can do better. So in order to take advantage of the extreme sensitivity to grain size that X-ray scattering has, why don't we just fit a parametric model where we can twiddle some knobs and see what works best? And if we're really good, we should really be using multi-wavelength information. So fit it all together in order to get the best possible understanding of our dust grain size distribution. So one of the things that I realized as I was creating my code and putting in these different pieces, that just by adding me scattering to my code, I got a lot of other information for free. And that's because fundamentally the scattering just relies on optical constants, and we have optical constants for a wide range of wavelengths. So just by putting in, you know, I have X-ray scattering halos, and then I put in my code, and all of a sudden I'm getting these nice optical depth plots versus wavelength from the infrared to the X-ray. So I said, that's cool, so maybe I can do something more with that. Okay, so in the switch from IDL to Python, it kind of drove the way I decided to develop the code. And I wanted to make it extremely modular. So the idea behind it is that I want people to use object-oriented programming in order to experiment with the models. So in general, in order to do that, a user would define a model as a Python class. And what the class has to do is have a set of attributes and functions that follow rules, which I'm calling the meta because I think it's a cool word. But I guess you could use another term like framework or something. But I like the meta. So here's an example from my library currently. There's a module called scat model that holds all of the scattering models that you might want to plug in. And at the top, there's a comment that says the meta, and it tells you what functions each dust scattering model needs to have. So for example, I have qsca, which is like the scattering efficiency, and it needs to take energy in terms of this units, and it needs to take another object called a complex index of refraction, which is in another module, and grain sizes. And then it also needs to have a differential scattering cross-section function, and then some of them can have other, like absorption and extinction. But in general, that's how you're going to be calling these objects. Here's an example of the simplest scattering model that I have in there. It's called PAH, and all it does is take a text file, so a table that was made by Drain for PAHs, and it reads it. So inside this getQ function, it says parse PAH, so this is a helper module that goes through the ASCII table and kind of breaks up the information. And then I say, all right, get the wavelength and the efficiency factor that I'm interested in, which is an input to this getQ function. And then it says, okay, now interpolate onto the energy grid that I want. And then at the bottom are a bunch of wrapper functions that call getQ for whether absorption, extinction, or scattering, whatever I want. Here's a very quick example of how you might use it. So here I make a grid of wavelength. Then I call the PAH model. I want neutral PAHs, i.e. they're not ionized. And then I have a little calculate albedo function where you take the PAH model, you get the scattering efficiency and the extinction efficiency, and you divide the two. Then I'm going to call that twice and make a big plot. Turns out PAHs don't scatter a lot, they just absorb. So in general, the idea is that then other modules that I use, so let's say I wanted to integrate up a whole bunch of different PAH sizes, I will send that to a different module that then calls qscat or qx a bunch of times, which is not the most efficient, but I'll work on it. But it calls that and then integrates it up. So I just want to go over my development plan that I hope to take this in the future. First of all, I really need to speed up my me calculation. So I've been talking to a few people about ways to do this. We were considering parallelization. That would help a little bit. But in general, the me calculation relies on a lot of for loops. And even if you're going, well, I mean, it's already been implemented in C and Fortran. But it can be implemented better with caching. Because basically, even for the C and Fortran codes, every time you call it, it does a bunch of for loops. And it's just not necessary. The other thing is I want to add other scattering algorithms. So there's some me scattering algorithms that aren't born in Huffman that are considered to be more accurate for the X-ray cross-sections in particular. But in addition, there's just new models coming out. For example, Drain just released an anomalous diffraction model, so I'm hoping to implement that in this as well. I do want to add parallel processing, so that's a thing that will happen hopefully in the future. But more importantly, I really want to expand the dust grain size library and add some parametric models that are more than just a power law. And finally, I want a bunch of optical constants. So this relies on laboratory astrophysics. And by giving those absorption cross-sections, you can calculate the fundamental constants and then do a bunch of scattering experiments with them. So I do have to say, I promise this will happen. It's a huge list, but I have grant money to do it, so it means I actually have to do it, which is great. Also, here's some fun things I would really like to make. I want to make a web tool that will give you an extinction curve based on whatever grain parameters you want to throw into a model. I would love people's input on as to whether or not that would be useful or helpful to them. In addition, we can make this web tool do high-resolution extinction cross-sections, for instance, in the X-ray. So this is a recent paper of mine where you see the optical depth as a function of wavelength for the iron L extinction edge. And if you add the scattering component, you get all these extra features that before people were just kind of ignoring. So that's something I want to do. But in addition, one place that I would really like this code to go is for us to sit down and think, what are the fundamental parameters of a dust library? Like, what's most important? Because if we can have a dust library in Python, we can do some other physics, like calculating the dust heating or the infrared emission. And these are all models that already exist, but it would be nice to have kind of a standard set. And then also something that you could do is calculate the radiation pressure on a dust grain, because it's absorbing a bunch of light. And that could be interesting for looking at outflows or how dust grains interact in star-forming regions and stuff like that. So one thing I could also envision with scattering codes is to expand them to other astrophysics applications. So for instance, when you look at an AGN or galaxy, host galaxy SED, you know that at the UV end of the spectrum, the intensity goes down because depending on your dust grain population or how obscured it is, it's going to absorb a lot of that UV light and then transfer that energy into the infrared. And I've had people ask me, what if my dust grains are large and gray? What is that going to do to my SED? And I said, well, I don't know because I don't really study that, but this could be something of interest to those people. Also, there's a ton of dust in planetary disks, brown dwarfs, and planet atmospheres, and scattering and absorption can be really important in those particular instances. So these are applications I'd like to see expanded. So I'm in the process of a major overhaul. I call it eblur dust because I was very uncreative in my initial naming of the dust codes. But I thought eblur, that kind of sounds good together, so there you go. So please fork me on GitHub. I really welcome collaboration and talking about where we want dust libraries to go. And that's it. I'll take questions. I'm very fast.
So I'm looking at the project right now, and how would you suggest installing, or are you considering maybe shifting over using package template? For...
Yeah, I'm gonna package it. It's on my to-do list. I should mention that all of that list of developments is a GitHub issue right now. So yeah, I could do it, and someone else could do it too. But I'm gonna package it.
Well, that was my question.
Any other questions? Yeah.
Have you advertised this at science conferences, and have you had interest in kind of people collaborating on the code yet, or
I have one or two interests here. I haven't really advertised it as a code visibly to the community. I think, especially with the proposal, I just kind of chose to advertise it then and see how it went. And the fact that it got funded, I was like, okay, great, this is gonna happen. So this is very much like a seed, but you're right, I should start advertising it to other communities.
So is your repository now the maybe best central location for getting all dust scattering tables, or is there another thing you should be linking to, or is there a central place we can go to get the constants that you're using?
Okay, so all of the constants, and there should be references in the doc strings. So many of the constants come from Drain's work. I showed the pH model, even though that relied on a table. That's the only one that relies on a pre-calculated table. That and the Weingartner and Drain models also rely on pulling some parameters out of a table, but you should be able to change them, I believe. I can't remember. But anyways, in general, the scattering stuff is calculated by the code. It's usually not calling in tables. It's just for different applications, like the pH thing. I was like, well, I don't need all constants for that.